with Asilata Bapat, talking about algorithms and computations with Bridgeland stability conditions.
Thank you. Thank you to the organizers. It's really a wonderful conference. And I realize that it's very broad, so I'll try to speak accordingly. But feel free to ask questions. So this is all joint work with Anand Deopurkar, who's at the conference also, if I can spell his name, and Licata. And I'll start off with just telling you what the objects are. And then I'll tell you what the ends are. So, so this is, at the moment, very broad. So suppose we have a group, G, super broad, acting on a category C. And the kinds of categories we consider are going to be suitably nice triangulated categories. Okay, and once we have this setup, the idea is that we can use some tools here to study various questions about the group action on the category. So the main tool that I'll talk about, which is in the title, is Bridgeland stability conditions. And the other tool, which is not in the title, is a restricted collection of objects in the kinds of categories we study, and these are called spherical objects. So these will show up again once I say more. But this is kind of the setup. And now, once you have a setup like this, I'll give you a flavor of the kinds of questions we're asking about these. And the kinds of questions are as follows. So if you have an object in your category, and you apply group elements to this object, so the group acts on the category, so it acts on the objects, so you can apply, so as we apply group elements, let's say 2x. So I guess what happens? So here are some possible questions. So maybe I'll say, how much can we, okay, so one, if x is some kind of complicated object, we would like to simplify it by applying group actions. So how much can we simplify x simply by applying group elements? Or we can try to go in the other direction. How much can we understand its group complexity? So if x is a relatively simpler object, if you apply group elements of x, how does it grow?
So can I ask, what is an action on a category? It's acting through an
auto-equivalences on the category. Okay. I'll say a little bit more in a minute. And then finally, I mean, these are just some questions that you might ask. So if we want to build a specific object of C, can we build it using a given object of C by applying group elements? So build some chosen object of C from X. You can ask many more questions, but these are the kinds of things. So when the group acts on the category, how can we study the evolution of objects under this action? Okay, so first of all, we'll need a few things. So we need some things before we can even start working on this. So we need, we need a category with a group action. So I'll say more about that in a minute. Whether a nice such thing exists and how does it exist and can we actually work with it. So that'll come later. But then we need some tools. So I said things like how much can we simplify X, how much can we understand its growth complexity. So we need some kind of measure of complexity on the objects of the category. So we need some way to measure how big the objects are. okay? And we'll also need, and this is not obvious, but it's convenient to restrict to some nice collection of objects, which I alluded to in the beginning. So I'll But I'll say something about this first, because this is what I want to showcase most in this talk, and this is a point of view that we've used a lot to study questions like this, and this comes from Bridgeland stability condition. So this is provided by. And I want to stress, so the aims of this talk are mostly to give you a flavor of these kinds of questions and how to compute with these measures of complexity that we get out of these stability conditions. And then if people want to use these in other settings, I would love to have a chat with you about it. And otherwise, I'll also say a little bit about the results that we found. Okay, so good. So let me start off with Bridgeland stability conditions. So don't worry, I'm not about to give the full definition. Maybe that is good news or bad news, I don't know. But I'll give some analogies. So, okay, so let me just say, let C be a triangulated category. And I'll give you a specific example a little bit later. If you've never worked with triangulated categories before, you probably have worked with abelian categories, so you should think of a triangulated category as something, the kinds of triangulated categories that I think about are categories that are tiled by abelian categories. So the standard picture that people draw is something like this. So this is supposed to be a picture of C, and inside of it there's some abelian category, and copies of A fill up C. So this is the kind of picture you should have in mind. So these triangulated categories come with a shift functor, and essentially all you need to know is this thing which is called with A, which is typically called the heart of a T structure on C, bounded T structure. And so if you're comfortable with abelian categories, that's fine. Otherwise, you can look at C. Okay, and then I'll tell you what a Bridgeland stability condition gives, and some extra data on C. And what does it give you? So a stability condition in this sense specifies, let's say, the following. And this is the point of view that I want to keep in mind. I sort of don't want to go into the full definition because we don't actually need it. So it specifies a list of stable objects. So actually I'll say a list of, I'll say semi-stable objects. Of C. So this is a particular collection of objects of C. And for those of you who are familiar with GIT stability, you should think of the semi-stable objects inside the abelian heart of C. Okay. And I'll highlight two other things which are important for this talk. So what happens to these semi-stable objects? So they have to satisfy various things, which I'll get to, but in particular, each semi-stable A, let's say, maybe A is a bad word, letter, X has a mass. So this is all part of the data, okay? So it has a mass, which typically my stability conditions are called tau. So I'll say m tau of X. This is a positive real number, and it also has a phase. And this is simply a real number. So if you're familiar with slope stability, then the mass and phase are typically combined into one thing called the slope, and the phase should be thought of as the angle of the object. Okay, so this is kind of this is a direct generalization of GIT stability. If you've never seen any kind of stability before, okay, so this is on this side of the board a complete analogy of the kind of thinking that I want if you've never seen stability before. So you should think of an analogy. Sorry. So this is not mathematical in some sense, it's analogous, okay? So this is an analogy of comparing C versus a vector space. Okay, so before I give this, I should say actually this plus several important compatibility conditions, which I haven't written, but I'll write one of them in a minute. Okay, so C versus a vector space V. Okay, so choosing a stability condition on C is kind of like choosing a basis for V. Okay, so stability condition, or shall I say the semi-stable objects, collection of semi-stable objects behaves sort of like a basis. So the important point is that there are many choices of bases on V, and what's the point of choosing a basis? It's not just any old collection of vectors, it's a collection of vectors that satisfies some like linear independence and spanning conditions, so that's similar to the conditions that these objects have to satisfy. And moreover, every object in V has an expression, a unique expression in terms of this basis, and that's the kind of feature we get here as well. So the key condition, which I'll write on the bottom, so the, among these compatibility conditions, there's a key condition that we'll use all the time, and that's the one thing you should remember. And this is the existence of what's called Harden-Arasimhan filtrations. So again, some of you may be familiar with this in potentially other contexts. So the idea is that not every object of C is semi-stable, that's just how it is, but every object of C has a unique expression of filtration with semi-stable quotients. And the filtration is unique in the following sense. So every X in C, whether semi-stable or not, has a unique filtration with semi-stable factors of decreasing phase. And this is sort of like every vector in a vector space has a unique expression in terms of the basis, and the key point that I want to make is that this exists, it's unique, but it depends on the stability condition. So just like the expression in a basis depends on the basis, so often a vector may be a basis vector in some basis, and it may be quite a complicated expression in some other basis. So that's similar to what happens here, and this depends heavily on the choice of tau. Okay, are there any questions about, this is sort of the key point, I'm not going to give any further definitions. This is it. Okay, so this is what we are about to exploit. So the Harden-Arasimhan filtrations of objects of our stability condition. And so now, actually, before I move on to telling you what the category is, let me point out that with this setup, we automatically acquire some measures of complexity. So you may already start guessing. I mean, every X has a unique filtration with semi-stable factors of decreasing phase. So you can count maybe the number of semi-stable factors that appear in X. If there are many, then that means X is a complicated object with respect to the chosen stability condition. So that's so you start acquiring some measures of complexity. Of X, let's say. So kind of the first one that you might think of is the number of factors in the HN filtration. So this, again, depending on tau. So for a fixed tau. You can do slightly more exciting things. So I mentioned that we have, for every object, every semi-stable object has these two numbers attached to it, the mass and the phase, and they're real numbers. So you can kind of start adding up some of these real numbers in various ways to get a real number as a measure of complexity. So what you can do is you could consider the mass. So a priori, I haven't told you what it is for objects that aren't semi-stable, but you can guess you can write it as the sum of all the masses of the semi-stable factors. So this is maybe slightly more refined than just counting the number of factors because it gives you a real number. And then you can start studying how this changes as you change the stability condition. So these stability conditions can be varied continuously, just like bases of a vector space can be varied, deformed continuously. So you can try to, as you deform bases, you might ask how does the expression of an element change, and that's the kind of thing you might ask here as well. Okay, and the third one that I'll consider, and I'm sure you can come up with many others, but anyway, the third one that I'll consider is the so-called phase spread. Sorry, this chalk is very of x. And I realized I don't have a notation for this, but it's okay. So the phase spread of x is simply you look at the factors in the HN filtration, the semi-stable factors in the HN filtration. Each one has a phase, which is a real number. You take the maximum and the minimum, and you take the difference. So that's so the difference between the max and min phases. Of the HN factors. But as I said, you could add them up in complicated ways. You can do some quantized mass. There are lots of other options. So you can choose your favorite. But all of these are very rich, and you can study them as you vary the stability condition, as you vary your object, And another key point that I want to make, so I guess this is another key point. I said it, but I'll write it again. So the HN filtration of X depends heavily on the choice of tau, and it's quite subtle as you vary tau, how it changes. So, so how the HN filtration changes vary tau is a subtle question. Okay. So, all right. So let me introduce the category that we mostly work with. And again, I want to emphasize that these methods might work in other settings, but this is the place where we chose to study them for reasons that will come up. So typically, I think about an algebraic description of this category, but sorry, is there a question? Oh no, sorry. Typically, I think of an algebraic description of this category, but since this is an algebraic geometry conference, I'll give you a geometric description, which is not what I typically think of, but it's perfectly valid. So let me just say, for the experts, we're interested in two Calabi-Yau categories. Okay, but the specific one that I'll say something about is the following. So let G be a finite subgroup of SL2C. So you might know that in this setup, you have what's called a Kleinian or Duval singularity. So we consider C2 mod G, the associated Kleinian singularity. We also have its minimal resolution. So in this setup, it's a very nice story. In this setup, the exceptional locus of this minimal resolution gives you a collection of P1s which are glued together or joined together in a configuration that's dual to the corresponding Dinkin diagram. So if you're familiar with the story, you know what I'm talking about. If not, we can just take this as a black box. So there is also an associated ADE Dinkin diagram. So normally there's an algebraic description which comes from this Dinkin diagram gamma directly. We can think about a more geometric description as follows. So we look at dbco of y. Okay, and then, so this is, I'm running out of board space, I'll come over here. So the category that we want is going to be a full subcategory of dbco of y consisting of objects.
So you might say what that is, not everyone will know what that is.
Of dbco?
Yes.
Okay, sure. So co of y is the category, abelian category of coherent sheaves on y. And db would be its derived version. So in the picture that I drew, I'll just label it here. So you should think here. So these would be coherent sheaves, category of coherent sheaves, and then db would be this big version. But unfortunately, I don't have time to say anything more than that. But as we'll see, it may not matter because, yeah, we'll see. Okay, so this is the full subcategory consisting of objects E such that E is supported on the exceptional fiber and the push forward, derived push forward of E along this map, F is 0. So that may or may not mean anything to you. That's okay. What do I want to say about this category? The main thing, so the main point to remember is that this category, I mean, despite appearances, is quite easy to work with. Okay, so I'll say that it's generated by objects which I'm going to call P1, P2 through Pn. And what's n? These are the vertices of the associated Dinkin diagram gamma. So gamma looks something like this. So this would be a type A Dinkin diagram. And there's one object, generating object for each vertex here. So it's generated by objects P1 through Pn, one for each vertex of gamma. Okay. So let me do an example on the side, which again won't mean anything for a little while, but will have that at least. So if you can think of gamma as the same one, no, maybe not the same one. I'll do A3 here. So that's the A3 Dinkin graph. And so the category C contains objects P1, P2, and P3, okay, which are one for each vertex here. And these objects are simple objects. Oh, this chalk is not, not my friend.
I
Sorry.
have some chalk for you.
Oh, that's okay.
I brought some good chalk.
Okay, well, I won't say no to that. Thank you. All right, so these are simple objects.
Chalk's
Oh, this is so much better. Thank you. In the abelian, standard abelian heart of C. So again, in that picture that I drew, this picture is getting a bit cluttered, so I'll draw another one. Okay, Same picture here. So there's a central piece, everything else is tiled by the central piece, and you think these objects P1 through Pn live here, and they're simple objects in that little category. So that category is generated by these simple objects. Everything else is kind of comes from shifts of these. Okay, so far so good, and so it's fairly concrete to work with because I'm about to tell you how these objects behave as well, a little bit. So not only that, what do I want to say here? Yeah, that's right. And the important thing is that each PI is a spherical object. So what does this mean? This means, in particular, that if you look at the object, now this is all living inside a triangulated category, so we have to look at, when we look at HOMs and endomorphisms, we have to kind of look at the total X algebra, which looks like a complicated thing, but the total X algebra of each of these objects is two-dimensional. And it says spherical because it looks like the cohomology of a two-sphere. There's something in degree 0 and something in degree 2, and that's all. So in a sense, these are quite controlled, simple objects in the sense that there aren't too many self-endomorphisms. Okay, so but these are the kinds of objects that I'll be interested in, and why is that? And I'm not sure if people can see if I write here, but maybe I'll just use the top board. So here's a fact. I guess originally due to Seidel and Thomas. And a spherical object, so if you have an object which is spherical in your category, gives you an auto-equivalence of the category. Okay, so if you have a spherical object X, you get an auto-equivalence, which typically it's called sigma X, which is known as the spherical twist in the object X, and it's an equivalence from C to C. Okay, so again, the important thing to remember is that our category is generated by these PIs, whatever it is, and each PI is a spherical object, and spherical objects give you auto-equivalences. So, okay, so that means each PI gives you one of these. And this is the origin of the group that's acting on our category. Okay, so I'll pause for a second to make some more space. If I could reach that, okay. So we were looking for a category with a group action, and these categories sort of automatically come with one. I mean, given any category, you can think of its group of auto-equivalences, but it's not. But unless you can find some nice elements in the auto-equivalence group, you can't really work with them. But here we have some explicit elements. Yes.
The simple ones are semi-stable for every stability condition.
No, unfortunately. So, okay, so that would be the case if you only looked at stability conditions, which are so-called adapted to the standard heart. But in general, we'll be thinking about stability conditions with any abelian heart, and then that's no longer true. So that's a good question.
I did it.
Yes.
So you denoted them by capital P, but they are not projective.
They are not projective. The reason people like to write P for them is that the algebraic description involves projective objects. So I think that's it. But they really are simple objects. So yeah, unfortunately a quirk of the notation. Any other questions? Okay, so now what do we get? So we've constructed well, for some definition there. I've given you some definition of a category C. We have a C. Again, given any category, group of auto-equivalences acts on C, but we normally don't have control over the group elements, and in this case we kind of do. So we also have distinguished objects. So we start off with these distinguished objects P1 through Pn inside of C, and we acquire sigma Pi. These are functors from C to C. Equivalences. So they're elements of the auto-equivalence group. So you can think of the group generated by these specific twists. And then you think about, okay, what are then the relations? These are some specific auto-equivalences. You find that these sigma Pi's satisfy the braid relations. So it's actually extremely nice, and I'll write them down. So I'm going to abbreviate sigma Pi by sigma I, just so I don't have to write that many P's. So this is if I is connected to J in gamma, you have this braiding relation, and otherwise they commute. So, in the case when gamma, for example, is our type A3 Dinkin diagram, the relations that these satisfy are the relations of the, always get this wrong, 4-strand braid group. So in this case, if you write down these relations for this graph, you get the 4-strand braid group. In general, for type AN, you'll get the, I think it's the n+1, strand braid group. And in general, if gamma is some other graph, it doesn't have to be a Dinkin graph, by the way. If it's some other graph, you'll get the corresponding braid group associated to the graph gamma, for which I've just given you the relation. Okay, so this is a very nice group.
But doesn't it, so that gives you S4.
So S4 has extra relations, which is that the square.
Oh, the square of the square. Yeah. Got it. Thanks. Okay.
It's a quotient. So that's not true in our case. Okay. So it's really the braid group that's acting, not the symmetric group. And now, so this tells you, so this implies that the braid group, which people will call, I call B gamma, which is, it depends on the gamma that you started with, acts on category C. And this is a rich group. It's really, really, infinite, first of all, but also has lots of rich structure, and people don't understand all of the structure in arbitrary type, and so there are lots of nice questions that you can ask about these group actions on the category. So you can ask questions about the category, you can ask questions about the group, and you can think about how they interplay with each other, and you can do lots of calculations, which I want to emphasize again. So, right. So this is now the setup. Okay. Oh yeah, and I should also say, once you have n spherical objects, the ones that we started with, you acquire tons more, because you can take, for example, P1, act on it by the spherical twist in P2, and that gives you another spherical object. So you can kind of keep acting. So let me just write that. Note, we also acquire lots of spherical objects. In C, starting from the PIs. So you can by applying sigma Pi repeatedly to other PJs. And let me write down some examples. Again, if you haven't done calculations in this category, may look, foreign, but at least it'll give you a flavor of what can happen as you start applying PIs to PJs. And this is something that is extremely computable. In fact, I've written some code that can compute it, so it's really very explicit. So even though it comes from some crazy looking category. Okay, so now, so here's an example. And remember, I want to, again, go back to this picture. The middle bit, the abelian category, consists of objects, well, it's generated by objects P1 through Pn, but in general, if you look at an object in the whole category, it'll look like a complex in the PIs. Okay, that's usually the structure of these derived type categories. You have complexes of certain objects satisfying certain equivalences, etc. But we'll write complexes for objects in this category. And so let me just show you what can happen. So for example, if I apply sigma P1 to P1, I don't preserve P1, but I shift it. Okay, so the twist in P1 applied to P1 itself shifts it from this piece here to one piece to the left or right, depending on your convention, but let's say one piece to the left. Okay, and so if I keep iterating, I'll just keep shifting. Okay, so not very interesting maybe. And now if I apply it to P2, I get something interesting. I get a complex that looks like this. I haven't told you how to do these calculations, so you'll just have to trust me, but this is what you get. And let me just say, now this is a little subtle, but I'll say it kind of in red so that we don't have to worry too much about it. But because of a quirk in the grading, this object, which looks like a two-term complex, actually lives in the heart of the T structure. So this object is in the abelian category. Believe it or not, I mean, it doesn't look like it. So there's a little bit of a grading quirk, which we have to deal with, but this looks like a two-term complex, but actually it lives in that shaded region. But now, if I apply it twice, I will now get a complex which looks like, and I'll write it suggestively like this. The notation is not fantastic, I have to say, but this is how it is at the moment. So I'm writing it this way to denote that this object P1 to P2, despite appearances, lives in the middle heart of the T structure, and this little piece here is kind of one homological degree away. So somehow the complex should be thought of as this object in degree -1 and this entire object in degree 0. So it's a little bit quirky, but that's how it is. But don't worry too much. I mean, this is to give you a flavor of what happens as we start applying twists to other objects. And now if I iterate this again, I'll actually attach another copy of P1 down here. So, and you might imagine what happens as I keep iterating. I'll get more and more copies of P1. Yes?
So what you're saying is essentially as you keep iterating, you get more complex diagrams.
Yes.
So this category has this ability to get, you have these diagrams that exist in this category.
They exist in this category and they get more and more complicated. Yeah. Yeah, exactly. And this is why this structure of the group action is so rich, because you can, start from sort of nothing and explode into, large objects. Yes.
I'm sorry to ask a trivial question.
No, that's okay.
The math from P1 to all these math from P1 to P1s are identities, right?
No, they're not. So this is the map, the degree 2 map that comes from the X algebra that I mentioned. So this is not the identity.
And the P1, P2 map is 0, of course.
No, it's not 0. There's a unique extension from P1 to P2 and also from P2 to P1. There's an X1 between P1 and P2 in both directions, and this is one of them, the correct one. But I didn't tell you that, so it's not clear. Yeah, so these maps are non-zero and not identity. Okay, so these are really, I think, okay, maybe I should say, the representations of these complexes that I've written are the minimal possible representations. You can't simplify these objects any further than whatever. Okay, so that's, but this is great because this is getting at the kind of the main point that I want to make. I mean, if you have this group action on this category, let's say, and if you have all these nice things like spherical twists and so on, you can start asking what happens when you iterate various group elements and act on objects in your category. So maybe I'll space up here as well. And now, okay, and now the question is, how do you measure how big an object gets when you do this? And the answer is, of course, these measures of complexity coming from stability conditions. So I'll explain that in a second. Before I do that, let me draw a picture of a stability condition on this category, to convince you that actually it's really not as bad as it seems, especially if you've never computed with these before. They are quite hands-on in this setting. Okay, so here's a picture. And it'll be good to have this picture in mind. I'll draw similar pictures later as well, but so here's a picture. And for simplicity, I'll take gamma to be A2. So I only have two generating objects, P1 and P2. And typically, people draw pictures like this. So you should think of, like, this is the upper half plane. Remember that every semi-stable or stable object comes with a mass and a phase, and so you can plop it down somewhere on the complex plane. So the idea is that you know, this is like, let's say, the phase of the first object, and this length is the mass of the first object, and so I'm going to consider a stability condition where P1 and P2 are stable objects, and the picture that I'll get is something like this. So this is convenient because then you can visually see what they look like. And it turns out that this third object, actually not this one, the other one, there's another semi-stable object in this whole story. And that's P2 to P1. So it's an extension between P2 and P1 where the quotient is P2 and the sub-object is P1. Okay, so so I claim that this gives you a pretty complete description of a stability condition on the category associated to the type A2 graph, if you like. And now, so this is simply a picture to keep in mind. And now we, what did I want to say actually? Let me think. Okay, that's right. So now consider, so this is tau. So this is fixed tau as an example. And now we can, okay, so now consider x and y spherical objects. So if you like, you can take x and y to be any of these objects. And now we start asking, you start with y, you apply sigma x to y, and sigma x squared to y, and sigma x cubed to y. And what happens? So how do you even ask a question like this? Well, you can use the masses that you had from your stability condition. So instead of asking, I mean, it's a little weird to ask, how do these objects grow? Because you have to have some like measure. And so the measure is given by the mass, for example. So you can start computing m tau of y, m tau of sigma x of y, m tau of sigma x squared of y, and so on. And just to give you a quick flavor of what happens here, how do you compute the masses? Well, the first thing you have to do is you have to compute its Hardy-Narasimhan filtration. Now, this takes a little bit of calculation, but it's not difficult once you really understand that picture. So in this situation, I'll circle the Harder-Narasimhan pieces inside these objects. So here, P1 to P2 does not appear as one of the stable objects that I've listed. It's not. And so its Harder-Narasimhan filtration consists of pieces P1 and P2. Okay. Here, I've got P2, P1, and another P1 in different degrees. And here again, I've got P2, P1, P1, and P. So in this case, the Harder-Narasimhan pieces are the ones that I've circled, and they're particularly simple in this case.
So those are the things you get after from the filtration.
From the filtration.
Right. So those are the pieces.
Exactly, yeah. So those are the filtration factors in the HN filtration of these objects. And so you can, and what's the mass? Then you add up the masses of these. And the masses are just now the lengths of these objects here. So whatever they are, you can add them up. And you notice you start with the mass of, you had the mass of P2, you add on the mass of P1, then you add on 2 copies of the mass of P1, and then you add on 3 copies of the mass of P1. So that kind of tells you the pattern. It's not clear why that should continue to hold, but the theorem is that it does. So, and it holds in a more general setting than the category that I've mentioned, but this is good to keep in mind as a concrete one. So here's the actual statement. So the statement is that if you take the tau mass of sigma x to the n of y, and you divide by n, and you take the limit, maybe n plus 1, doesn't matter. And you take the limit as n goes to infinity, this actually stabilizes. And it stabilizes to one of 2 things. So, if y is not x or any shift of x, then you actually get the following. You get the mass of x times the dimension of the total x Hom, I don't know, from x to y. If y is not a shift of x. And otherwise you get 0. And let's just verify. The same thing happens, if y is a shift of x, so for example, P1 is a shift of P1, you apply sigma P1, you get another shift of P1, you apply it twice, you get a shift by 2. If you divide by n, it's going to go to 0. The mass will go to 0, because the mass of the shift of any object is the same as the mass. And so when you divide by n, the left-hand side here goes to 0, as it should. On the other hand, if you think about applying, for example, sigma P1 to P2, you get this behavior where you start with P2, and then you pick up copies of P1 as you keep going. And in the limit, at the nth step, you have like n copies of P1 basically. And so in the limit, you get the mass of P1 times the dimension of the total Hom space between P1 and P2, which is 1. So that's illustrating that behavior. But this is more general, and it holds for any 2 spherical objects. So that x and y. So this is kind of telling you growth complexity, and immediately raises some questions as well. I've managed to tell you something about what happens when I iterate a spherical twist, but I haven't told you anything about what happens when I iterate a general group element, which is not a spherical twist in general. So again, immediately some questions. What about other group elements? And we don't have a good understanding of this yet. We can say something, but oh, I've already broken this chalk. Whoops. Okay. Okay. And one remark that I'll make. Actually, maybe I won't even write it. But the one reason to study this, apart from the nice calculation aspects of it, is that these kinds of limits end up giving you some points at the limit, as limits of stability conditions. And this is a nice thing to study. You have the space of all stability conditions, and this kind of gives you points in the compactification. So that's also nice. Okay, so that's sort of a side remark.
Excuse me. So these are elements of the ring.
these are elements of the braid group as acting on the categories. So functors on the category. That's right. Okay, so, and now I'll say one other thing in the last 10 minutes, I think, if I can find it.
So I wanted to just ask a quick question.
Oh, yes, of course.
So in the theorem on the board, I'm not quite sure if you mentioned this earlier. Are there any conditions in the Bridgeland stability condition, or any Bridgeland stability condition?
That's a great question. Any Bridgeland stability condition on this category. And as you can see, it's sort of, the stability condition kind of now hides in the background, even though that you started with that.
Okay.
So if for example, in that theorem, if you divide both sides by m tau of x, you get a statement where the right-hand side does not depend on tau. Yeah. Okay. Okay, so here's a fact which I'll mention without proof, but it's very useful. In these kinds of categories, the HN filtration factors of a spherical object X are also spherical. Maybe I'll call it Y. So this is also a really nice reason to kind of restrict to spherical objects. I mean, not only do we have spherical twists, these objects are kind of closed under HN filtrations in some sense. So it's a nice collection of objects to restrict to, and it gives you nice results as well. So now we ask the opposite question. So can we simplify by applying group elements? Simplify Y by applying group elements. Again, elements of the braid group. And you might start again guessing the answer to this question, because you know this is what happens when you iterate spherical twists. You start picking up tails of P1 or P2. So maybe to simplify, maybe you're supposed to do the opposite thing, whatever that means. But it turns out that actually works. So here's another theorem. Okay, so Y is now a spherical object, and tau is a fixed stability condition. Again, it can be any stability condition, no restrictions on C. Now let X be the HN factor of Y with the topmost, highest phase among all the HN factors of Y. And I'm sorry, I should say it be the spherical. I mean, I'm about to use this. HN factor of Y with the highest phase. Okay. You can do the same thing for the lowest, respectively lowest. So in this case, for example, P1, here, this P1 is the spherical HN factor of lowest phase. This P2 is the spherical HN factor of highest phase. Okay, so that's how it sort of goes. So it turns out you can undo the effect of X on Y. So, for example, here, if I had gone ahead and applied sigma P1 inverse to this object, I would have gone back to P1 to P2, which is kind of a smaller object in some sense, and then doing another sigma P1 inverse would have sent me to P2, which is again like kind of squishes the object down again. So that's the idea. So if X is the spherical HN factor of highest, respectively lowest phase, then the phase spread of, get this right, sigma X of Y, and respectively sigma X inverse of Y, is lower, smaller, than the phase spread of Y. So just to, so this object has quite a large phase spread because it has P2, P1, and then this P1 lives in a smaller degree, so it's kind of spread out over a larger numerical range, I don't know. And then as you apply, in this case, if you apply sigma 1 inverse, so it's the inverse twist in the bottom phase, you kind of decrease the phase, and the same thing would have happened if you had applied sigma 2 instead, which is the spherical twist in the top object. So somehow you can, given an arbitrary spherical object, you simply observe its top and bottom Hn factors, and then you kind of strip off the effects that they've done, and you shrink the object. So I'll give you one picture, which is slightly more complicated than the one I drew there, just to give you an idea of what kinds of things happen. So here's a picture for gamma equals A3. So again, I have to get the lengths and phases right, otherwise it won't work out, but it's all kind of drawn on the board anyway, so. So the key, by the way, the trick here in this is that you can just, you can put P1, P2, and P3 wherever you like. And that determines uniquely a stability condition. And then the other objects, you can figure out which ones are stable. So that's what I'm doing. So I've put P1, P2, and P3. They're always stable, as someone mentioned. They're always going to be stable in this kind of stability condition. So I put them wherever I like, and then the other extensions, I post hoc I figure out which ones are stable. So so in this case, it turns out that the other extensions that are stable look like P3 to P2, P1 to P2, and the way I'm drawing it, you'll see, the vectors add up as well, so that's nice. And then finally, I don't know if this will fit on the board, but there's a third one, P1 to P2 to P3. Okay, so this is a complete list of stable objects up to shift for this stability condition. And now, let me take as my object y, I'll take the object P2 to P3 to P1. So this is some other extension between P1, P2, and P3. And if you do the kinds of calculations that the idea basically is, if you want to figure out its Hn filtration, how do you do it? You try to break it up into pieces, where each piece has to be one of these stables, and you do it in such a way that the order is correct. And there's a unique way to do it, so eventually you'll find it, and you can be more systematic if you like, but the Hn filtration pieces in this case are P2, P3, and P1. Okay, so now the bottom Hn piece is P2. Okay, it has the lowest phase, and so what I can do okay, so actually, sorry, before I do that, so notice, what is the phase spread? It's the phase difference between the phase of P2 and the phase of P1. So it's this angle here. Whatever that amount is, that's the phase spread. Okay. Now, X is P2, and my algorithm is telling me that I have to apply sigma inverse of X to Y. So I do that. So I've already done this calculation, so I know what it is. And it's this kind of extension. And now once again, it's the same game. I have to now break it up into pieces where the pieces are among the pieces listed here with decreasing phase in the appropriate way. And it turns out, I'll finish in 1 minute. It turns out that the pieces in this case are P1 to P2 and P3. Okay, so that's how it breaks up. And as you can see, it drastically changes as well. So the new phase spread is this. So it's shrunk. And this always happens, so you keep shrinking. So this is great. This is great. I'll end on a kind of unsatisfying note though. This is great, but it's great if it terminates. So it's subtle because the phase is a real number and the phase spread is a real number. And great, I'm lowering the phase spread, but by how much? I don't know. So here's a question. So actually, question, what about termination of this algorithm? So the idea is that I want it to terminate when I have a single HN piece. So that is when I'm semi-stable. But in general, we don't know how to answer this. In finite ADE type, the answer is that it terminates, but otherwise, we don't know. Okay, and I'll say one more thing before I end. Okay, so these are the kinds of questions that we're answering with this setup. You can ask and answer lots of other questions. So for example, you can ask, if you apply a group element, if you do something, what happens to the HN? How do the HN filtration factors change? How can you predict what will happen as you apply group elements? Again, in general, we don't know what to say, but in type A2, which is a very simple example, we have a finite automaton that describes the whole process. So it's very well understood, so you can really, yeah, but still it's kind of a piecewise thing. You have a finite automaton, but I won't say anything about it. But there are lots of questions, especially in general, about these growth rates. Okay, I'll stop there. Thank you.
Are there any questions?
You wrote down essentially two ways on the blackboard for generating new spherical objects out of old, in particular starting from the simple ones. One is applying the spherical twist break group, and the other is picking a stability condition and looking at the factors of the harder Epsilon. Are there specific stability conditions where you're sort of getting the same correlation?
That's a great question. Actually, in these categories, there's a third result which I didn't mention, which is if you start off with a stability condition that you like the way I did it. So put P1, P2, and P3 wherever you want, and then you have to figure out which other objects are stable. So we actually have an algorithm that tells you which objects will be stable. And that we can do it by applying break. So if you arrange P1, P2, and P3, or Pn in any way you like, you can then, there's an algorithm that generates all the stables, or a stable object of a prescribed class in the growth and need group, if you like, and it tells you which group elements you have to apply to generate that. So actually there's a connection between those two as well, so that's nice. But yeah, again, more generally, I don't know how to do that.
So here, in the theorem, so is it implicit then that the HN factors of a spherical object are also spherical?
Yeah, so this is, I wrote this up here. So it's a fact about two Calabi-Yau categories.
Oh,
So you need, this is a little subtle, you need this extra condition that I didn't really say anything about. But
and in this example, so you start off assuming that P1, P2, and P3
are
stable.
stable. Yes. So yeah, so one thing.
In the heart.
That's right. So I'm looking at a stability condition which is adapted to the standard heart. Now P1, P2, and P3 are simple objects in the standard heart, so they're automatically stable.
And just one last thing.
Sure.
What does this notation for Y mean?
I always struggle with this in myself. I mean, okay, so it means that it's an extension, complicated extension between these three. So the quotient is P2, and it has two. The sub object is like P1 direct sum P3. As a complex, it looks like this, but it happens to be an object that's in the heart of the D structure. I can tell you more. I can tell you more. Yeah, it's a little it's hard to say on the board.
Are there any other questions? Okay, let's go.